Sorting is one of the most basic and frequent problems you will run into in computer science. In its most basic form, sorting is when you are given a list of numbers and you would like to sort them in numerical order. Let's start with a very basic example of sorting, using an algorithm we call bubble sort. So imagine you are given a set of cards and you would like to sort them in numerical order. Using bubble sort, what we would do is we would compare two adjacent cards, and then if one is greater than the other, we swap them, slowly but surely creating a sorted list. For instance here, we compare two cards, and if the card to the right is greater than the card to the left, we don't do anything. However, if the card to the left is greater than the card to the right, we swap. However, this is a very naive way to sort, and there are much better ways. Let's take a look at a better way, using this algorithm, which is called heap sort. In heap sort, we essentially build a max heap and then delete all of its values. So we are given an array to be sorted, and we use the space of this array to actually store the heap itself. Heap sort is what is called an in-place algorithm. In other words, it only needs a fixed amount of memory along with the memory used to store the data in order to run. So we build a max heap, delete the REUP via swapping with the last leap, and then recalculate the heap. We do this a number of times until we eventually have a sorted array. Let's move on to a more famous sorting algorithm called quicksort. The way quicksort works is it picks a partition, usually the first to the last element in the array, and then putting all elements smaller than that partition to the left and all elements greater than that partition to the right. It will then recursively call this partition on these smaller and smaller subarrays before it builds the whole array back up, creating a sorted array. This algorithm has one fatal flaw though. If it is given an already sorted array, it'll have to make a partition on every single element of that array, which ends up making this case as slow as bubble sort. How do we get around that? Well, in 1997, a computer scientist named David Musser took these two algorithms, heap sort and quicksort, and invented a hybrid algorithm, intro sort. What intro sort does is it takes the partitioning idea from quicksort and it partitions down into the array to a depth of 2 times log n before switching to heap sort and building heaps out of these partitions and then sorting these heaps. This is very stable because of the heap sort and very fast because of the quicksort. So here we have some visualizations of these algorithms in play. This is quicksort, and you can actually see how it's partitioning the array into these subarrays before sorting them. Once again, this is a very, very fast algorithm and is very popular among many computer scientists, but it does suffer from a flaw. That being, if there is already a sorted array, then it has to make a partition on every single element, which is not very efficient and can actually make your runtime as worse as bubble sort. Here is heap sort, a very stable version of a sorting algorithm. However, it's not as fast as quicksort, but its worst case is also as good as its best case, so it's reliable even though it's not as fast. So if we take these two ideas and we merge them into what is intro sort, we get the speed of quicksort with the stability of heap sort, and you can actually see the partitions being heapified in the top left here. Very, very stable algorithm. And finally, here's bubble sort. A pretty naive solution. This is actually sped up to twice the speed, while the other ones were 1/10 the speed of the original sorting speed. Overall, I think it's quite clear that intro sort is one of the best sorting algorithms because it combines the speed of quicksort with the stability and security of heap sort. I hope you guys enjoyed the video and learned all of this in constant time. Thanks.